Hello everyone, welcome to Vedantu JEE English. Okay, if you can hear me, if you can see me, just type in clear. If you can see me, if you can hear me, type in clear. Today is very important topic and we are going to be dealing with this, and almost we will be completing the semiconductors. Logic gates, I'll be doing it in the next class. Logic gates, I'll do it in the next class, and with some PYQs also. If you can hear me and if you can see me, just let me know. We'll just start the lecture. If you people can hear me, hi Arvind, Rajesh Arvind, hi, Mr. Hacker, hi. Okay, Hacker has said that it's clear. Okay, now let's start. Let's start then. So every one of you know this thing that we have launched the JEE crash course. Those who are interested, right? Those who want regular classes to be conducted, and every day DPP is being given, and every weekend a test has to be conducted, such that a proper schedule and all those things. Those who are in need of it, we can enroll for this. It's going to be taught only in English. Okay. Now, as usual, we are going to start with the semiconductor. Today, I am not using the Node 3 app. Generally, the letters are going to be a bit bold in that. Today, I have taken up some of the animations, or you can say simulations. So, using those simulations is going to be helpful only in the PPTs. If I am going to be converting those PPTs into PDFs, no, those simulations are going to be converted and those simulations won't work. That I don't know, Arvind, how much cost for the test series, I don't know. You can just go through the Vedantu website, you'll find out. And Shushmita is asking, sir, when will you do fluid mechanics? Let's see. We are sharing the topics. If fluid mechanics comes under me, then I'll do it. Sir, when is thermodynamics and KTG lecture? I think it should have been already done, right? By Shreyas sir, it should have been already done. Okay. Now, look. How do we classify a material as a conductor, as an insulator, as a semiconductor? Like, what is the basis for categorizing the materials into these things? So, one basis is going to be band theory. So, before we go and deal with the band theory, let us just talk about a single atom. When we have a single atom, when we take a single atom, and that atom is going to be having electrons revolving around it in orbits, right? Electrons are going to be revolving in orbits. So I'm just, for namesake, I'm drawing one electron, but there will be many electrons. Now, for example, for you to understand, for example, let us take the energy of this electron to be some minus 13.6 electron volt. Let us just take it. Don't think that, sir, minus 13.6 is for hydrogen atom, right? There will be only one electron. You have drawn multiple electrons. I'm just randomly taking some number. If you want, I'll change it also. That's not a big deal. Okay. Now, I'll take one more atom, which is going to be very same as that of this left side one. Then, in that also we will have electrons. And the energy of this electron will obviously, for example, the energy of this electron will also be minus 13.6 electron volts. Now, if I start bringing these things closer, then what will happen? You only visualize, if I start bringing these two atoms closer, then first these two green orbits, whatever are there, first they will meet. If I further take them in, then even these orbits will meet. If I further take them in, then even the internal, the lower, like even the this smallest orbit, whatever is there, even they are going to be meeting. So when the atoms are going to be taken very close, when the atoms are going to be taken very close, then the orbits are going to be overlapping. As a result, electrons are going to be shared by the atom. Now look, if electrons are going to be shared by the atom, then according to Pauli's exclusion principle, no two electrons should have all the four quantum numbers the same. Then we can't have two electrons being exactly sitting at the same energy level. That's what the Pauli's exclusion principle says indirectly. You can have, if two independent atoms are going to be taken, then you can have electrons, multiple electrons having same energy level or occupying the same energy level. But when you have made them come closer, for sure they should not be occupying the same energy level. Then what is going to happen? Here I am just talking about what? I am just talking about just two atoms. But if I am going to be talking about a solid, we will have many atoms, right? We will have, if you take a solid, we will have many atoms. That means it's not just two atoms which are going to be coming closer and not two electrons having same energy levels. We will have some lakhs of electrons which are going to be occupying the same energy level, which is not allowed. If we have 1 lakh of atoms which are independent, 1 lakh of electrons will be having same quantum number, but they are in different atoms, so they are allowed. Now when those 1 lakh atoms are going to be put together, when one is influencing the other, in that situation those 1 lakh electrons can't have all the four quantum numbers the same. As a result, the energy level whatever is going to be there, it gets split into very fine energy levels, and those energy levels it gets split into is going to be taken as band of energy levels. Is going to be taken as band of energy levels. For example, look, so if this is going to be the separation between the atoms, right? So as the separation decreases, if the separation is big, you have 1s, 2s, 2p, all those things are going to be there, right? These are those energy levels, 1s, 2s, 2p, those energy levels. Now, as the separation between two atoms is going to be decreased, first the outermost ones are going to get affected. Now there are many electrons which are occupying this state, but once the distance is going to be decreasing, the electron starts getting shared. As a result, that energy level will split into many fine energy levels, and all these energy levels put together is going to be called as band of energy levels. So one single energy level will get split into very small energy levels, like small gap energy levels, accommodating all the electrons which are supposed to be having same energy. Why? Once those electrons are shared, as I said, once those electrons are going to be shared, no two electrons should have all the four quantum numbers the same. Then that energy level gets split into many small energy level gaps, and all those energy levels will accommodate those 1 lakh of electrons. So if you are going to be decreasing the distance even further, even these energy levels are going to get affected, and they are also going to get split to accommodate all the electrons and to make sure that they are going to be having different quantum numbers and different energy levels being occupied. Okay, fine. Next, if I further decrease the space between the atoms, if I further decrease the space between the atoms, even the innermost orbits are going to get affected. So even the innermost energy levels have to get split. Have to get split to accommodate all those electrons. So when you bring in the atom so close, as the space keeps decreasing, first the outer orbits are going to get split. As you further decrease, the inner orbits are also going to get split. Why the energy levels have to get split into many energy levels? Because they have to accommodate all the electrons which were previously occupying same energy level. When they are present in different atoms, now they are shared, so they should not occupy the same energy level. As a result, the energy level gets split. This is called as band theory. Now, based on this band theory, for example, let us take this to be the separation of atoms, or you can say interatomic distance. Then you take one level, it got split, and then let us take one more energy level, which got split. Let me just extend these things. So we have these energy levels. Now, if I am going to talk about this particular interatomic distance, let us take it to be some R0. This is a particular interatomic distance. It's a particular interatomic distance. For that particular interatomic distance, you can see some blue energy levels. And then you can see some gap between the yellow energy levels and the blue energy levels. Those are the energy levels which are not occupied by any of the electrons, and this is called as the energy gap. In fact, it is called as the forbidden energy gap or forbidden energy levels. All the energy levels at this location, or you can say in this gap, whatever the energy levels are going to be there, none of the electrons are taking them. Either the electrons are present in these energy levels or the electrons are present in these energy levels. Now we are going to name this as valence band. We are going to name the yellow one as valence band, and we are going to name this above energy levels, all those put together, called as conduction band. Okay, fine. Now, based on this energy gap or the forbidden energy levels, we are going to classify the materials. So for conductors, what was observed? For conductors, that energy gap is close to zero, or conduction band and valence band are overlapping. Conduction band or the valence band are overlapping. What does that mean? Look, this is the conduction band, and as I said, very fine energy levels. That single energy level gets split into very fine energy levels. That means the energy gap between these levels is going to be what? Very small. So a small increase in temperature also can easily make the electron go from this level to this level, and then next level to the next level, like that easily. Once the electron is going to be there into this conduction band, it can easily jump from one level to the other level because the energy gap is very small. Now, as I said, in conductors, the valence band and the conduction band are going to be overlapping, right? And valence band is the band where those valence electrons are going to be there. Now these valence electrons, for these electrons jumping from one level to the other level, it's not a big deal, right? Because the energy gap is very small. As the energy gap is going to be very small, these electrons can easily jump from these yellow levels to the blue levels, and then in these blue levels they can aram se move. So it's very easy for the electrons to move from one energy to the other energy level. That's why we say in conductors we have free electrons. Why we say free electrons? Because those electrons which are going to be there in the valence shell, those are the last electrons. So that valence shell electrons, whatever are there, all of them, whatever the energy levels are going to be occupying, that we are going to call as valence band. I think Akshara have answered your doubt. Okay, now look, those electrons which are there in the valence band are going to be overlapping with the conduction band, and you can see very fine energy levels. So electron can easily jump from this level to 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 this level, like that it can aram se move inside the conductor. That's why the movement is way easier in conductors. Now, sir, what if they are not overlapping? Semiconductors. So if the energy gap is less than 3 electron volt, then the conduction, you can clearly see if there is energy gap and it is less than 3 electron volt. We have valence electrons, obviously, or you can say in the valence shell we will have electrons. Now these electrons, to become free, all the way they should jump an energy gap which is less than 3 electron volt. If they go here, that is when the electron can aram se freely travel in this entire conduction band. Once it is going to take this leap, once the electron gets an energy which is going to be, let's say, more than 3 electron volt, it can aram se go to the conduction band, and in the conduction band, as the energy levels are very close by, so it can easily jump from one energy level to the other energy level, and the electron is free to roam around. So always keep in mind, if someone is going to use a word saying that there are free electrons, yes, when they use the word free electrons, according to band theory, those are the electrons which are going to be in the conduction band are the ones which are called as free electrons, because there are many energy levels and they are not already occupied by the electrons, so the movement is easier. If they are already occupied by the electrons, then you have to think about whether they are going to be having same 4 quantum numbers the same or not. But most of the conduction band is going to be what? Those energy levels which are present for the outermost orbits. What is valence band? Valence band is the energy levels that have been given for the valence shell electrons, right? Okay, now these valence shell electrons, if they go into the conduction band, then they are free. When I use the word free, they jump into the conduction band. Keep that in mind. Okay, now what will be called as insulators then? What will be called as insulators? What will be called as insulators? If the energy gap is going to be more than 3 electron volt. So in that situation, right, it is very hard for the electrons to gain 3 electron volts of energy and go over there. So barely any electron will be able to any electron will be able to get barely any electron will be able to go to the conduction band. So there will be almost no electrons. There will be almost no electrons in the conduction band. Sir, why did you use the word almost? Why didn't you say that there is no electron at all? Always keep one thing in mind, there will be some super excited electrons, very few super excited electrons which will have lot of thermal kinetic energy. Might be 1 or 2 electrons go into the conduction band, but it's fine. Those 1 or 2 electrons will not contribute for any amount of current. That current generation is very, 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 very small. Okay. Sir, explain one more time. Which part? Which part? Which part? Okay. Okay, I'll do it. I'll do it. I'll do it. Once again, roughly I'll do it. I'll start from here, right? So you know that there will be lot of energy levels where there will not be any electrons. There will be lot of energy levels. There will be lot of energy levels where there will not be any electrons at all. Where there will not be any electrons at all. Right? We have electron here. Let us take. We have electron here. Right? We have electron in these shells. Right? S orbital, p orbital, and all those things. I hope you people know that from chemistry. Let us say in these orbits we don't have any electrons, and wherever the last electrons are going to be there, that energy level or those things are going to be called as valence shell. Those electrons are going to be there in the valence shell is what we say. The last electrons are going to be called as the valence electrons, and they will be present in the valence shell. And above that also we have energy levels. Keep that in mind. But there are no electrons in those orbits. Keep that in mind. Now, if I take one more atom which is going to be similar to this, as I start bringing closer, first what are the levels which are going to be interacting? First, what are the levels which are going to be interacting? Obviously, when I am going to be bringing them closer, the outermost ones are going to be interacting, right? You only visualize. As I start bringing them closer, first these two will interact. Now, that energy level, whatever is going to be there, has to be split into many energy levels. Although there are no electrons, if electrons are going to be there, they have to accommodate all those electrons, but not in the same energy level. That's why the energy level, single energy level, whatever is there, will get split. So splitting of the outermost will happen. You further move closer, then splitting of this also will happen. You further move closer, then splitting of this also will happen. So all those energy levels which got split, where there are no electrons at all those energy levels put together, we call them as conduction band. Right? And for you to understand, I have taken just 2 atoms, but in reality, when you take solid, there will be many atoms which are kept very close. So there will be many electrons which are going to be shared. Many electrons are going to be shared. To accommodate all those electrons, definitely the energy level has to split into many energy levels. And how it splits? It splits into very fine energy levels. What is meant by very fine energy levels? The energy gap is going to be very small. Now, as I said, first you can clearly see when the separation is big, this is the one which got affected first. As you keep decreasing the separation, then the inner orbits also. As you further keep, even more innermost orbits also got split. Right? Now, I'm just taking a situation. Look, I am talking about The last orbit where the electrons are there, or those shells, valence electrons are the ones which are going to be there in those last orbits. Beyond that, whatever orbits are going to be there, I am going to call them as conduction band. Wherever the last electrons are going to be there, that is what I am going to call as valence band. Right? Now did you understand what is now I hope you people clearly understood what is called as conduction band and what is called as valence band. As I said, as you start taking the atoms closer, the single energy level gets split. Single energy level gets split. All those energy levels which got split and where there was no electron at all, those outermost orbits whatever are there, all those energy levels put together we call as conduction band. And as you further decrease the distance, definitely wherever electrons are there, those orbits are also going to be interacting with each other. As a result, that energy level also should get split. So wherever that last electrons are going to be there, that energy level when it gets split, it will also become into band of energy levels, and that band is going to be called as valence band. Now I think everyone are clear with conduction band, valence band. So if the energy gap between these two, like for some material, there won't be any energy gap only. They will overlap. And those materials where they are overlapping, we call them as conductors. Where the energy gap between them is less than 3 electron volts, those materials will be called as semiconductors. If the energy gap is more than 3 electron volts, then we call them as insulators. And as I already said to you, these are the energy levels which are not taken by any electrons. That means they are forbidden energy levels. They are not supposed to take. So either electron can exist here, the electron can exist here, or the electron can exist in this conduction band. It can't exist in between. If any electron is able to go to the conduction band, then we have lot of finely divided energy levels. So this electron has lot of space to roam around, but this electron, no, it doesn't have lot of space to roam around because already there are electrons which are filled. So if this electron wants to go down, there is an electron already filling that place. So the electron which is already sitting over there will not allow it to move. But an electron which is going to go to the conduction band, no electrons are there because these are all the outermost orbits which got split. So it can easily move around, but that ease of movement will not be there for these electrons because already the energy levels have been occupied. That's why an electron which is going to go to the conduction band has lot of places to sit. So it can aram se freely move around. That's why we call this electron as free electron. No. See, Minuhu is asking why gaps are there between them, sir. Nature. You don't think why the gaps are going to be there. It is because of the interatomic distance. See, if the interatomic distance between those materials is going to be, let's say, for example, somewhere over here, you can see the valence band and the conduction band has overlapped. If the interatomic distance is going to be this, then I can see the gap. So naturally available materials, if you take, depending on their interatomic distances, we have those gaps. So naturally available. So we have silica, we have carbon, we have sodium, we have ferrous. So like that we have, right? So those solids when you take, they are existing like that. And then we classified them. As I said, if the gap is less than 3 electron volts, semiconductors, more than 3 electron volts, insulators. That's it, done. It will be boring for others. I hope, Minuhu, your doubts are clarified. Now look, first of all, why are we in need of semiconductors? Why do we need semiconductors? To be precise. Exactly. Spartan, yes, you have to listen to, man, because I might add some depth. Okay, fine. Now when I'm going to talk about semiconductors. First of all, why do we need semiconductors? Look, there are some situations where we need controlled flow of electrons. We don't want flow like conductors. Conductors will allow huge amount of electrons to pass in very less amount of time. Insulators, they won't allow electrons to move only. We want something in between. That's why we are going to be talking about semiconductors. All the electronic devices, whatever we are using, have semiconductors in them, because they don't want a perfect conductor which will allow huge amount of current to flow. As a result, the circuit gets fried up. We need a controlled flow of electron. In fact, we can say we need the flow of electrons which are going to be accounting for milliamps of current. Electronic devices need milliamps of current only. They don't need 1 ampere, 2 ampere, 3 ampere. Okay. Now, that's the reason why we need the semiconductors. First, just search in the periodic table which elements are going to be having that energy gap less than 3 electron volts. That carbon, silicon, germanium, that group are perfectly fitting in. So then let us take, for example, silicon. Silicon is going to have 4 valence electrons. All the silica atoms are going to have 4 valence electrons, and all those 4 valence electrons are going to be shared with the surrounding ones, and they form a bond. The name of the bond, I hope you people know it. The name of the bond which arises from the sharing of electrons. Okay, fine. So they are involved in bond. Now what I'll do is, I'll give energy to these electrons. How? Sir, how we will give energy to those electrons? Let's say I'm heating it. I'm giving thermal kinetic energy. So when I am going to give energy to this one, when energy is given to that electron, then that electron which is there in the valence band has got energy. Now it can become free and go to the conduction band. So when I use the word electron is becoming free, when I'm going to use the word electron is becoming free, my intention is it has moved to the conduction band. Keep that in mind. Okay. Now, hi Mr. Sanjay. After a long time you have come, I guess, to the live. Or might be you have kept quiet. Okay. Now look, because of me giving energy to that electron becomes free. That electron gets free. Okay, fine. Then what will happen? As that electron gets free, there is absence of electron over there. There is absence of electron. And what happens to the bond? Okay, that absence of electron, we have a special way to represent it. We represent it with a symbol like this, and we call it as hole. Hole is nothing but absence of electron. And now you tell me how we have to visualize this in terms of band theory. Now look, I'll show you this situation. This is the conduction band, right? This is the conduction band. And this is the valence band. And in the valence band, we have electrons. And in the valence band, we have electrons. Now what happened? One of the electron one of the electron has become free. One of the electron has become free. So that electron has now gone to the conduction band, and now aram se it can jump in that conduction band. There is no restriction at all. From wherever that electron has left, there is an absence of electron. A vacancy got created. Now those surrounding electrons, whatever are going to be there, those electrons which are there, some of these electrons can go to the place where there is absence, right? So if the electron is going to go over here, then there is absence of electron here, the hole moves here. If this electron goes and fills that whole place, then there will be a hole created here. So because of the movement of electrons in the valence band, we feel that the hole is moving. Actually, movement of hole is nothing but what? Absence of electron is moving. So basically, this movement is very much restricted. Unlike the movement of this one, this can go wherever it wants, no restriction at all, because all the energy levels are free. But if you talk about the movement over here, already we have pre-existing electrons, so the movement is going to be restricted to some extent. Now we have a vacancy, so this electron can go over there. If the electron is going to go over there, then hole is going to be coming to this place. Do you want to see how it looks like here? Look, if this electron comes and fills the vacancy, then what will happen? Then the hole is going to go here. The hole gets transferred here. So now if you see, the current in the semiconductors is going to be because of two things. One is going to be movement of this free electron. One is going to be because of the movement of the electron in the valence band. In both the situations, it is electrons only which are moving. But I want to clearly differentiate between both of them. So instead of electron movement, here I will call it as hole to be moving. Actually, in reality, who is moving? Electrons only moving to the place where there is absence of electron. Here also electron is moving, here also electron is moving. You will get confused. That's why from now on, whatever the electron is going to be moving in the conduction band, I'll call as free electron movement. And whatever the movement of electrons are going to be there in the valence band, there instead of saying electrons are moving, I'll say hole to be moving. So the total current is going to be because of the hole movement, and it is going to be because of the electron movement. When I say because of the electron movement, it is the movement of the free electron. When I say current due to the hole movement, it is because of the movement of the electron in the valence band. In both the situations, it is electrons which are moving. I will be teaching logic gates also. But you have to be patient. I'll come there. Now look, I have a simulation for you. Yes, electrons are going to be shared, then you get the bond, right? Now you look, as I said, you can see the hole is traveling. You feel that the hole is traveling. Actually, who are moving? Electrons are moving. And what are those electrons? Those electrons are the valence shell electrons, are the electrons present in the valence band. Once again, one last time, let this get zoomed in. Look, you feel that the hole is moving. But in reality, what is moving? The electrons in the valence band are moving. Keep that in mind. So clearly, to differentiate between two types of movements, what we have come across in electrons, one we say electron movement which has moved to the conduction band, one we will say hole movement rather than saying movement of electrons in the valence band. Keep that in mind. Okay, now so in these intrinsic semiconductors, we will have any number of electrons, you can say, per unit volume, or you can say electron charge density, NH, number of holes per unit volume, and I am going to say Ni, which is called intrinsic charge carrier concentration. Intrinsic charge carrier concentration. So the relation between them is Ne into NH is going to be Ni square. You might think, sir, what are the intrinsic charge carrier concentration? Man, you got electrons and holes created, right? Electrons and holes together, put together, is going to be called as intrinsic charge carriers. Intrinsic semiconductor charge carriers. So if you are going to be talking about their concentration per unit volume, if you write it as Ni, Ne into NH is going to be equal to Ni square. It's an important result you people have to keep in mind. For intrinsic semiconductor, obviously, how many our electrons are going to be there, those many holes are going to get created. So Ne is going to be equal to NH. So if you are going to put it into this, then you get Ne square, or you can say NH square is equal to Ni square, indicating Ne is equal to NH is equal to Ni. Just keep this in mind. But this is an important formula not only for intrinsic semiconductors, even for extrinsic semiconductors also this formula is going to be holding good. Sir, what is intrinsic semiconductor, sir? Purely if you have everything to be silicon atoms, it's called as an intrinsic semiconductor. Purely if the whole solid, whatever you have taken, is having germanium in it, then we call them as intrinsic semiconductors. You have taken a solid, all the atoms in the solid are silicon. It's called intrinsic semiconductor. But the problem with intrinsic semiconductors is they didn't meet our expectation. Intrinsic semiconductors didn't meet our expectations. See, we were in need of certain amount of conductivity. Not like conductor, not as bad as insulator, but we were in need of certain amount of conductivity. Intrinsic semiconductors are not meeting our expectations. They have less conductivity than what is needed. We have a problem, man. We have a problem. What is that? If I talk about my mobile phone is in need of a controlled flow of electrons, and it demands certain amount of conductivity. Intrinsic semiconductor didn't meet that. Okay, fine. Then we go for extrinsic semiconductor. Extrinsic semiconductors. So how these extrinsic semiconductors are going to get formed? By doping with impurity. What is doping? What is this process of doping? Man, you are going to be replacing one of the silica atom with some other atom, which is going to be either aluminum, or you can say trivalent impurity or pentavalent impurity. Trivalent impurity or pentavalent impurity. So if doping is done with trivalent impurity, If doping is done with trivalent impurity, then we call it p-type semiconductor. We call it p-type semiconductor. Man, what actually happens? I'll put it in layman terms. What happens? I'll put it in layman terms. So basically, one silica, which is going to be what? Having 14 protons and 14 electrons is replaced with aluminum, which is going to be having 13 protons and 13 electrons. 13 protons and 13 electrons. That's how it's going to get replaced. Right? Now, what happens when we remove one of the silica and keep aluminum? Aluminum has only 3 valence electrons, right? So, the moment I am going to be drawing aluminum, aluminum has only 3 electrons. Aluminum has 3 electrons. And if I am going to talk about silica, silica has 4. Silica has 4. So if this aluminum has to form bond with the right side silica, it doesn't have the electron to share. It doesn't have electron to share. Here, no problem. Here, we have a problem. Here, no problem. Here, no problem. As I said, we have a problem, right? We have absence of electron to form this bond. So the moment you have done the doping, from the starting itself, we have some holes pre-existing. Now look, what will happen? Some of these electrons, like for example, the one which is involved in the bond over here, will come over here. Then the hole is going to go over there. And again, this electron can go over there. Then the hole will go over here. So, in the beginning itself, without making any of the electrons free, we have a hole created. Now, if I give some thermal energy and make this electron free, then one electron becomes free, but we have 2 holes. As a result, what will happen? The conductivity has increased or not. We have increased the freedom for the movement of the electrons. So when compared with the intrinsic semiconductor, extrinsic semiconductor is better. Right? I think I would have taken, yes, you can see. They have put with boron. Look man, there is a hole and the hole is moving. There is movement of hole, and one more thing. Okay, let me just show you one thing. Look, hole movement. When they are going to zoom out, now focus on. Let me focus. Look, here we have electron involved in the bonding actually, but that electron has become free. Once again, this is something which I have already explained. Look at we have electrons here, and that electron has become free. That means we have heated and we have created one free electron. There also a hole got created. So, in p-type semiconductors, the population of holes will be more than the population of electrons. And one more thing. Sir, you are talking about replacing the silicon atom with aluminum atom. How many such replacements have to be done in order to meet our expectations? Parts per million. That means every 10 power 6. You can replace 1 or 2 silica atoms and done. They meet our expectations. So doping is not going to be too high also. Keep that in mind. Don't think that, excuse me, out of every 10 silica atoms, 1 atom is going to be replaced with aluminum. No. If I do doping in parts per million, that means for every 1 million of silica, if I replace 1 or 2 silica also, it is meeting my expectations. Dark night I'll be taking only on Friday. It will be a 3-hour class, and yes, I'll be doing fluid mechanics this coming Friday. And okay, fine. So what we realized here is that the number of holes are going to be more when compared with the number of free electrons, right? And keep one thing in mind. Keep in mind, doping is going to be done, in ppm, parts per million. That meets our expectations. And at equilibrium, roughly NH into Ne equal to Ni square holds good. So even for extrinsic semiconductors, you can use this formula, right? Let us not dig too deep into it, not needed. How much ever is needed, that much I am giving you. I hope everything has been put logically. Now, let's see for p-type semiconductor. Let's see what happens. For p-type semiconductor in band theory. Look, man, we have conduction band. Right? And for intrinsic semiconductor, no energy levels are existing in this gap. These are all forbidden energy levels. But now, when I replace silica with boron or aluminum, that atom which I have got into the material, into the solid, that allows some energy levels. Whatever the impurity I have got, that impurity allows some energy level close to the valence band. That's the reason why whatever the electrons were existing here, they got bit freedom to move because more energy levels are available. You came in with holes, so those electrons are going to go. As a result, hole movement is more, and these energy levels are called as acceptor energy levels because they accept electrons. These energy levels are going to be called as acceptor energy levels. Yes, there can be a theoretical question. What type of theoretical question? When we do doping with a trivalent impurity, where extra energy levels are going to get created close to the valence band. Radhika Rani, thank you. Where is it? Oh, I have done this. Acceptor energy levels are going to get created in terms of band theory. Now, I have a small question, man. Is p-type semiconductor positively charged or negatively charged? Is p-type semiconductor Positively charged, positively charged. Is p-type semiconductor positively charged or negatively charged? Is p-type semiconductor positively charged or negatively charged? Come on, respond. Most of the people, they see this word, they see this P, and they'll be like, okay, P-type semiconductor is positively charged. No, man, it's neutral. See, Jay Morgan is asking a question, why are say sir don't teach in JEE crash course? See whether it is going to be, I think he's busy, just like me. Like, I'm not teaching in the crash course of Infinity 2.0. Same is the case. But definitely justice will be done to you. Whoever are going to be teaching, they will definitely have a very good conceptual understanding. Okay, fine. So P. Generally people think it's positively charged, but actually the P-type semiconductor, but actually it is neutral. But actually it is neutral. But actually it is neutral. Why? Use your common sense, man. What did we do? We have taken silica, which was having 14 protons and 14 electrons, and we replaced it with aluminum, which is having 13 protons and 13 electrons. So a neutral atom has been replaced with a neutral atom. Then why the body is going to get charged? Just because it has more number of holes, don't think that it is going to be positively charged. This is one common misconception most of the students have, and I have cleared it. It's neutral. We take out an atom, we keep an atom. An atom we have taken out, neutral. The atom we have put in is neutral. So nowhere it is getting charged. Okay. Take a question then. The acceptor level of a p-type semiconductor is 6 electron volt. The maximum wavelength of the light. The maximum wavelength of light which can create a hole would be, they gave this much energy. So if this energy is given, a hole gets created. So 6 electron volts energy has to be given. So the energy of the photon we are going to be supplying should be 6 electron volt. Then 6 electron volt, energy of the photon is hc by lambda. They asked us to take hc as this. So 1242 eV nanometers by the wavelength. Now that EV can be kicked out. So the wavelength is going to be 1242 by 6 nanometer. So 1242 by 6. 1242 divided by 6 is going to be what? 207. 207 nanometer. So which option? D option. Okay, fine. Next, N-type semiconductor. And let me be honest with you, in industries, majority of the times, if they have to choose a single semiconductor, they will prefer N-type semiconductor. Why they will prefer N-type semiconductor? I'll clearly explain. If they have to if they have to talk about choosing 3 out of which 2 of them should be one type, then they will take NNP. So transistor, NPN transistor is widely used in industry, but not PNP transistor. Why? We will get to know now. Pragya Pinniti is asking, does IIT toppers go beyond the syllabus, that is university level? I have a small thing to answer for this. If your aim is going to be less than 500 rank, then you don't need to go. If your aim is going to be being in top 10, then people are going to be learning something extra, or below top 15 JEE advanced. Then if your aim is below 500, just learn whatever is there in the syllabus. That's more than enough. Okay, fine. Now When do we get n-type semiconductor? If doped with pentavalent impurity. So for example, let us take, we doped it with phosphorus. And we know that phosphorus has 5 electrons in the valence. So we have silica. Okay, okay, okay. We have silica. Okay, 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 and okay. Now, what will happen is that when we dope with phosphorus, 4 electrons are involved in the bond. It's bit hard for us to break the bond and make the electron free. But there is one electron, one fellow who is not involved in the bond. That fellow can easily become free. This fellow, this electron can easily become free. What has happened, man? If you give slight amount of energy also, this is going to get free. If you give slightly more extra energy, then the electron which is there in the bond also becomes free. Then if this becomes free and the one which is involved in the bond also becomes free, then what will happen? You have 2 electrons, but you have created only one hole. You have created only one hole. So in n-type semiconductor, who are the majority charge carriers? Electrons. So electrons are going to be more in population. So that's why we call majority charge carriers. Majority charge carriers in n-type semiconductor are electrons. Majority charge carriers are electrons. Which part? Vasu Ratnam, which part? I can redo it if you want. Which part? Okay, fine. Now look, this is phosphorus. That fellow can easily become free, and you can see I have given extra energy. 1 second. This electron can easily become free, right? And look at this, bond is broken, electron becomes free. As a result, hole gets created. So there will be hole movements also, there will be electron movements also. There will be hole movements also, there will be electron movements also. Man, if you need, you know the place where you have to go and search. I'm not here to give guidance. You know where to search, man. Vasuratnam. Go and search. You know where to find. Okay. Now, sir, that Ne into NH is equal to Ni square. Is it going to be still valid? Yes, roughly it's going to be valid. So still you can use Ne into NH to be equal to Ni square. Okay, fine. Now, sir, can you explain whatever has happened in terms of band theory? Can you explain whatever has happened in terms of band theory? Okay, look, let's try understanding. See, in reality, if only silica is going to be there or silicon is going to be there, you will have energy levels which are allowed to be taken by the electrons, these energy levels, and we will have valence band energy levels. So because of me taking this phosphorus in, there is this extra electron, right? So that extra electron should occupy some energy levels or not? That extra electron should occupy some energy levels or not? Which energy levels that electron is going to be occupying? It will be occupying energy levels which are close to the conduction band. Right? So that electron, whatever I was talking about, is there in this band. All the electrons, I'm not talking about a single electron because I'm going to dope with many phosphorus atoms, right? So there will be many electrons. All of them are going to be very close to the conduction band. So they can easily enter into the conduction band. If they are able to easily enter into the conduction band, they are able to become free easily. That's what I have explained. Nah? It's very easy to free this electron. That means easily it will enter into the conduction band. Why? All those electrons are going to be present very close to the conduction band, they become free. And these are going to be called as donor energy levels. These are going to be called as donor energy levels. Okay. Now we have dealt with the p-type semiconductor, n-type semiconductor. We have understood how that electron has become free and how it is able to move freely. In terms of band theory also we have learned it. Now let us do questions. This is a question from NCERT. This is a question from NCERT. Suppose a pure silica crystal has 5 into 10 to the power 28 atoms per meter cube. So how many are there? 5 into 10 to the power 28 atoms of silica per meter cube. These many are there. Now what they said, it is doped by 1 ppm concentration of pentavalent AS. It is doped by 1 ppm concentration of pentavalent AS. 1 ppm means what? Every 10 to the power 6, for every 10 to the power 6 silica atom, we are going to put 1 AS. So every AS I am going to be putting is going to have 1 electron extra. Right? Okay. Pentavalent, right? So we will have 1 electron extra. So how many such electrons are there per meter cube? So in 1 meter cube, I have 5 into 10 to the power 28 silica. So how many pentavalent impurities are going to come in 1 meter cube? So that is going to be, see, it is going to be 5 into 10 to the power 28 divided by 10 to the power 6, which is going to be 5 into 10 to the power 22. So these many are there. These many AS are there. That means those many electrons are extra. Now apart from that, whatever the electron which is involved in the bond, if that breaks, then 1 electron and 1 hole gets created, right? If it has become free, as a result 1 hole got created. So because of doping I have these many electrons extra, and because of doping, we have 5 into 10 to the power 22 electrons free or almost free. Because of bond breaking. How the bond is going to get broken? we give thermal kinetic energy, as a result it is going to break. So because of bond breaking, let's say X holes and X electrons get created. X holes and X electrons get created. X holes and X electrons get created. Now, just a second, man. I need one more slide. Okay. Now we have a formula. What is that formula? Ne into NH is equal to Ni square. Did they give Ni value? Yes, they have given. 1.5 into 10 to the power 16 is what I can see. 16 or 18? Okay, I'm just writing it to be, okay, for your clarity, I'm just writing this. I'm just taking it to be 1.5 into 10 to the power 18. I'm just taking it. It's not clear. I'm just taking 1.5 into 10 to the power 18. Okay, fine. How many electrons are there? Because of doping, I have 5 into 10 to the power 22. And because of bond breaking, I have X electrons more which got created. So I can say 5 into 10 to the power 22 plus X. And how many holes? X is 1.5 into 10 to the power 18 square. Man, okay, let me write it. Let us use our common sense. Let us use our common sense once. 1.5 into 1.5 is going to be 2.25. 2.25 into 10 to the power 36. You can see this is 10 to the power 22. Then what should be the order of X such that we get total order to be 36, 10 to the power 36. It means roughly this X should be in terms of 10 to the power 14 or not. That means if this is in the order of 10 to the power 14, whether you add this X or not to 10 to the power 22, will it make much of a difference? No. X is in the order X in the order of 10 to the power 14. So 5 into 10 to the power 22 is way big when compared with X. That means I can roughly write that whole thing to be what? 5 into 10 to the power 22 into X is 2.25 into 10 to the power 36. So what will be the X value? As it is roughly 5, 2.25 divided by 5 is going to be how much? 5 4s 20, 0.45. 0.45 into 10 to the power 14. So you can say X to be how much? 4.5 into 10 to the power 14. So I can say that roughly how many electrons are going to be there? Roughly we are going to have 5 into 10 to the power 22 electrons and holes to be how much? 4.5 into 10 to the power 14. Netra aspirant. I don't know which chapter, man. I have to see because I have come in between, right? If it is going to be in Vedantu Telugu JEE, I know what I am going to do because I started it. But this is something which I haven't started. So I have to talk to Sway sir regarding that. But anyway, way ahead, you are going to see the thumbnail in the video section. Now, did you understand why people say Ne is way big when compared with NH in N-type semiconductor? Look, the power of it is 22 and the power of holes is 10 to the power 14. And do you know what is the doping? Doping is just 1 ppm, man. If you do doping of 1 ppm also, look at the huge difference between the number of holes and number of electrons. Okay, so keep these things in mind. This is one question which was troubling me when I was doing my 12th. When I see these kind of questions, I used to be I used to freak out. Now I have shown you how to do them. Okay, now look, let us talk about diodes. Basic theory of semiconductors has been done. Now we have to talk about diodes. What will be the use of diodes and all those things? In this class itself, we are going to talk about that. And as I said, I will end the lecture when I am going to be done with Zener diode. Logic gates, and some of the PYQs, whatever are there, I'll be picking up in the next class. Okay, because I have to complete semiconductors in 2 classes. There is no point in me giving lot of theory in less amount of time. Okay, now look, what is a PN junction diode? Look. I'll change the color. See, the reason why I have chosen PPT today is that already you should have realized I have taken some simulations, and to understand this PN junction diode, I have taken even more simulations. You have lot of simulations coming up. Look. You have next. Right? So that's the reason why I have chosen, I'm forced to choose PPT, because if I convert this into note, then none of those simulations will work. Okay, fine. Let us take this to be the P-type semiconductor. And in P-type semiconductor, what are we going to have? We are going to have lot of holes. And those who are thinking that, sir, are we going to have only holes? No, in P-type semiconductor, holes are the majority charge carriers. Electrons are the minority charge carriers. Yes. Now, I'll take N-type semiconductor. If I am going to be choosing the N-type semiconductor, in N-type semiconductor, it is exactly the reverse. We have lot of electrons, and electrons are the majority charge carriers. And we will have holes also. It's not that there won't be holes at all. There will be holes, but they are minority charge carriers. Now, I just want to ask you a small question. In chemistry, you would have come across this. What is it? If you are going to be taking one room filled with, let's take the room we are sitting in is filled with oxygen, and the next room is filled with hydrogen. When you open the door between the rooms, what will happen? Diffusion of gas. Why diffusion is taking place? In one location you have huge number of oxygen molecules, on the other side we have hydrogen. What did I say? Hydrogen. Ranjani, the class has started at 5:30. Okay. The moment we open the door, some oxygen goes that side, some hydrogen enters this side, because it has to balance out the concentration. Concentration should look same throughout. That's what that process is called, diffusion. Now the same thing is going to happen when you are going to be joining one P type and one N type, because N type has lot of electrons and P type has lot of holes. So diffusion takes place. As a result, what will happen, man? Due to diffusion, electrons from N move to P, to the P-type semiconductor. Arey, do you know what is exactly happening over there? If electrons go this side and holes go this side, if electrons are going on to this side, now the P-type will be negatively charged. And when holes go that side, N type will be positively charged. Now there is charging thingy which is happening. Okay, fine. Let us see what happens. This is what happens. P and N are brought together. Holes are represented with white dot. Electrons are represented with those green dots. Now diffusion takes place. You see what is happening. Diffusion takes place and you get a region where there won't be any charges at all. A region gets depleted of charges. It looks something like this. And what happened over here? Yes, this location has more negative thingy, and this is going to be, you can say, positively charged, and as a result there will be an electric field which is going to get established. Okay, E is not visible. If I draw green, is green visible? No, that is also not visible. Is blue visible? No. Okay, I'll take white only. Now let us look at this electric field. So what that electric field does? That electric field is from N side to the P side. As a result, if any hole wants to go to that side, hole you can treat it as a positively charged kind of thing. Then on the hole there will be force like this. And if any electron wants to go from this side to this side, electric field is to the left side, so force on the electron will be to the right side. So these majority charge carriers are discouraged, and those majority charge carriers, for the movement of the majority charge carriers, this region is discouraging them and acts like a barrier. And you can see in this region is depleted of charges. That's why it is also going to be called as depletion region. Okay, fine. That and all is fine. For majority charge carriers, it's a discouragement. Agreed. But what about minority charge carriers? In P side, the minority charge carriers are electrons. So for minority charge carriers, force will be to the right side. That means the minority charge carriers are encouraged. Minority charge carriers are encouraged. So this thing results in what? Results in a region which will be depleted of charges. That region, let me just draw like this. This region is called as depletion region. Depletion region, right? And what kind of electric field got established? If you remember, there was an electric field which got established like this, which is discouraging. The E discourages movement of majority charge carriers. And for minority charge carriers, it's a downhill journey. Why it's a downhill journey? What happens when you're going down the hill? You don't need to do anything. Automatically you'll go down, you'll roll down. That's what is happening over here. Sir, now I have a doubt. Sir, do you mean to say that minority charge carriers are going to be moving in the PN junction diode? If minority charge carriers are going to be moving, then there should be some current. And the current that is associated with minority charge carrier movement is called as drift current. Sir, do you mean to say that there will be current? Do you mean to say that there will be current? Yes, due to minority charge carriers, yes, there will be current. But if you talk about the overall current in the PN junction diode, when it is not connected to anything, is zero. At equilibrium, the total current is zero. Sir, on one side you are saying that there will be current due to the minority charge carriers, and on the other side you are saying that the total current is zero. Yes, I mean it. Why? On this side, yes. Can you see, once the depletion region got formed, can you still see, once the depletion region got formed, can you still see some white dots going to that side? Once the depletion region got formed, can you see some white dots and can you see some green dots going this side still? So what are the white dots? White dots are the majority charge carriers. Although the depletion region got formed, still some of the majority charge carriers will be able to cross the depletion region. Sir, why? Arey man, always there will be exceptions. What are those exceptions? There will be some majority charge carriers with high energy. Even the depletion region is not able to stop them from crossing. Majority of them are stopped by this depletion region, but there will be some majority charge carriers with huge amount of energy. They can be stopped. As a result, even at equilibrium, even at equilibrium, the diffusion current, even at equilibrium, diffusion current not equal to zero, drift current not equal to zero, the total current is going to be zero. What does that mean? Diffusion current and drift current are cancelling out each other. Okay, look, let me draw that. So we have this region to be the depletion region, and we have this side to be P, this side to be N, and the minority charge carriers here are going to be electrons, here holes. So how are they going to move? How is the drift current? Pakka, the drift current is going to be like this. And majority charge carriers, holes, right? Holes move this side in diffusion, right? So still there will be some high energetic holes which can go to that side. So there will be some diffusion current. There will be some diffusion current. Even once equilibrium is attained, this will cancel out this. Magnitudinally, the diffusion current is going to be equal to the drift current. This much conceptual clarity you will not get anywhere. And with this kind of simulations, I have spent time, although this is not the first time I am using these things, already I used this in Vedantu Telugu JEE channel, right? So then at that point of time, I have spent a lot of time on making these slides. Okay, now look. So what we realized is that there is an electric field, right? So let me draw that electric field. So this is the depletion region, and in that depletion region, we have an electric field, because of which there will be a potential difference, and that potential difference is going to be called as barrier potential. And now, if you are going to be talking about what will happen when we move from P side to the N side, will the potential increase or will the potential decrease? Majority of the people think that P means positive, N means negative, and as a result, people say that when you move from P to N, potential will decrease because from P we are moving to N, which is negative. Nonsense. When you are moving from here to here, you are moving opposite to the direction of electric field. Pakka potential should increase. So if I'm going to talk about this barrier, in that barrier region, if you start with a potential somewhere over here, that potential should increase. You can see the potential is increasing. Why? We are moving opposite to the electric field. So if you talk about a PN junction diode, this depletion region is the barrier for us, man. It's a barrier. It is not allowing majority charge carriers to move. If majority charge carriers don't move, current will not exist. So somehow we need to get rid of this barrier, and that barrier is demanding some potential. If the barrier potential, let's say, is 0.7, if I am going to connect this to a battery of 0.7, then this 0.7 will be cancelled out by the potential of the battery. As a result, this depletion region won't exist. Okay, fine. Next, how do we practically represent this PN junction diode in reality, in the experiments or in the circuital diagram? So this will be the P side, this will be the N side. Keep this in mind. This is how we represent the PN junction diode. So the whole thing has been explained with simulations in this PN junction diode, right? Now let us talk about forward biasing and reverse biasing. So before we go for that, what I would like to show you is that, look, we have the region, depletion region, and in the depletion region there is electric field, because of which there is some electric field. If I am going to be connecting a battery like this, what this battery does, the battery will establish an electric field which is going to be like this, because this is at higher potential. P side is at higher potential, N side is at lower potential. So the battery is trying to cancel out this electric field. And what this electric field is doing, this electric field is trying to stop the majority charge carriers. So once the battery is going to come in, this depletion region is going to be made thinner and thinner and thinner. Why? Now these majority charge carriers got support. So these majority charge carriers are going to be breaking into this depletion region. As a result, the size of the depletion region keeps decreasing as I keep increasing the voltage. And at one particular voltage, it will be able to completely break this depletion region, and the depletion region no longer exists. Aram se freely the majority charge carriers can move. Okay. What happens, and when you do this, this is going to be called as forward bias of diode. So if you maintain the positive side at higher potential and if you maintain the negative side at lower potential, we call it as forward bias. Now the very same situation, if you are going to be maintaining exactly the reverse way, we have depletion region and we have E. Now we connected battery in the reverse way. Then this one is maintained at lower potential, this one is maintained at higher potential, P is maintained at lower potential, this is maintained at higher potential. So the electric field by the battery is also encouraging the minority charge carriers, but discouraging the majority charge carriers. So the barrier, or you can say the depletion region, becomes bigger in size. The barrier becomes bigger for majority charge carriers because even battery is opposing them. So this becomes bigger. But keep one thing in mind, for minority charge carriers, it is downhill journey. So minority charge carriers are even more encouraged. Here in forward biased, majority charge carriers are encouraged. Majority charge carriers are encouraged. And in reverse bias, what is called as reverse bias? Whenever you are maintaining P side at lower potential, N side at higher potential, that's what we call as reverse bias. Okay, fine. In reverse bias, what is happening? Minority charge carriers are encouraged. But anyway, the current due to minority charge carriers is very small. Fine. Now let us look. You already have a rough idea about forward biasing. You can see when the switch is closed, the moment switch is closed, you can see the majority charge carrier started moving. First, when the switch is closed, one second, you see switch is open, barrier is there. As the switch is closed, the barrier slowly decreased and no longer the barrier is existing. And once the barrier is not going to be existing, the majority charge carriers are going to move. If majority charge carriers are going to move, we call that current to be diffusion current. Right? So, because of this battery, diffusion current has drastically increased. Drift current, obviously, if majority charge carriers are encouraged, minority charge carriers will be discouraged. Keep that in mind. Exactly, they are opposite. Okay, now okay, I already explained. Now look, what is happening when we keep increasing the voltage, the forward voltage. What is that forward voltage? This battery. This, you write V forward voltage. Battery's voltage. As we keep increasing the battery's voltage, depletion region slowly decrease, and at for one particular forward voltage, depletion region didn't exist at all. That's when drastically the current should increase. You can see over here. The current was very small because depletion region is there. As I keep increasing the forward voltage, at this particular value called as knee voltage, from there onwards, you can see the current has drastically increased. So the diode is going to send the current drastically, allow the current drastically in the sense, don't think that 100 amps, 200 amps. When I use the word drastically, previously it was 0, now it will be in terms of milliamps. That's it, right? And that knee voltage for germanium is 0.3 and for silica it's 0.7. For germanium it's 0.3 volt and for silica it is 0.7 volt. And one more thing which you have to keep in mind is that once the knee voltage is attained, more or less the voltage is same, but it can take any amount of currents. I hope you people can clearly see that. So once the diode starts conducting, almost the potential difference across it will remain to be the knee voltage only, but it will allow huge amounts of current to flow. So if they specifically mention diode, for example, if they say it is a silicon diode and if they say that it is conducting, then the potential drop across this should be taken as 0.7 volt. If they are going to draw a diagram like this and if they are going to say that it is germanium, then the potential drop across this should be taken as 0.3 volt. If they don't mention silica or germanium, if they don't mention which diode they are talking about, then please don't take any potential drop across that diode. Okay. Now, reality is this, but as I said, you can talk about something called as dynamic resistance. So what is the dynamic resistance? For same change in potential difference, you see the change in the current. For same change in potential difference, here this much is the change in current, here this much is the change in current. So here there is more current and here there is less current. So the resistance is going to change or not. That's called as dynamic resistance. And the dynamic resistance, normally resistance is going to be what? V by I, right? So the dynamic resistance is going to be the change in voltage by the change in current you have created at that location. You just have a rough idea about it. And one more thing, I said once the depletion region breaks, huge flow of current is what I said, right? What I used, right? When I say huge flow of current, my intention is milliamps. Just keep that in mind. My intention is milliamp. Just like conductors, semiconductors won't allow huge amounts of current to flow. When I say huge amounts in semiconductors, my intention is always milliamps. Man, what random thing there. Okay, I hope I have clearly explained the forward biasing. Just take a small question on this. First of all, are they forward biased? You can see the P side and this is the N side. P side is connected to the positive terminal of the battery. The N side all the way goes like this and connected to the negative terminal. So these are forward biased. As it is mentioned clearly, germanium, you take 0.3 volt, silica 0.7 volt. So once there is a potential drop or potential difference of 0.3 and 0.7 across this, then current flows through this. What is the total potential drop across this one? 1. So rest of the potential drop will be across this, right? So what is the total potential drop across this? The total potential drop across this is going to be 14 volt. So it is going to be I multiplied with the resistance, which is 4 kilo ohm, is 14. So the current is going to be 14 by 4 milliamps. Now what are they asking? What are they asking? They are asking the voltage across the load resistance RL. So the potential drop across the load resistance is going to be current multiplied with the load resistance, which is going to be 14 by 4 multiplied with 2.5 kilo ohms, and milliamps will cancel out. As a result, what are you going to get? 14 into 2.5 divided by 4, which is 8.75. So it is 8.75 volt. If they haven't mentioned what diode it is, then please don't take any drop. You take the drop to be 0. That means they are neglecting. Okay. Now, the reverse bias thingy. What is that reverse bias thingy? I already explained to you. If the P side, we have this to be the depletion region. If the P side is connected to lower potential, higher potential, this is the P side, this is the N side. We have already a pre-existing electric field in the depletion region, and even the electric field of the battery is also going to be like this. As a result, drift current increases drift current increases and diffusion current decreases. So current flow will be due to minority charge carriers, and that current is going to be in microohms. If when majority charge carriers are contributing for current, if they are going to be in milliamps, here minority charge carriers have downhill journey, and that downhill journey will correspond to what? Minority charge carriers, and they are very few in number, so the current has to be evenless. Current has to be evenless. So if I am going to be plotting a graph, that graph is going to be something like this, and then we will have all of a sudden huge amount of current, and it is called avalanche breakdown. So what happens? And one more thing, almost the current was zero till that point of time, but it is not exactly zero, almost it is zero. Why? Because there will be definitely some contribution by the minority charge carriers. When you apply electric field like this, for minority charge carriers downhill journey, for majority charge carriers uphill journey, so majority are discouraged, minority are encouraged, so slight current will flow. But something extraordinary, not extraordinary in fact, something dangerous is happening at one particular voltage, man. And at that particular voltage, I can see huge amount of current to flow all of a sudden. Why that current is flowing? What is happening? Why it is called as avalanche? Okay, look. Minority charge carriers are accelerated too much. As a result, they gain enough kinetic energy to break. Okay, once again, they gain enough kinetic energy to collide with electron in bonds and free it. One fast moving electron goes and knocks out the electron which is involved in the bond. Now what happens? We have two electrons. These two will create 4. 4 will create 8. 8 creates 16. And there is fast moving and a lot of collisions. Whenever collisions are going to be there, there will be heat which is going to get generated. 1 becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16, and all these are going to be having collisions. So the diode gets heated up, the diode gets destroyed. Now you should understand why it is going to be called as avalanche. If you know an avalanche, it starts small. As it goes down, it accumulates more and more snow and it becomes big. That's what is happening. It starts slow. Minority charge carriers, they are very few in number, but they gain enough kinetic energy and they become dangerous. They collide, break the bonds, more electrons becoming free, more dangerous electrons getting free. And these electrons again go and strike. Like that, the whole diode gets destroyed. How it looks like? Look at this. I don't know whether you can see it or not. Started as a small thing but ended as a big one. Started as a small thing but ended as a big one. That's why it's called avalanche breakdown. What happens in avalanche breakdown? Yes, one electron becomes 2, 4, becomes 8. Normally, whatever the electron is going to be coming, if they are not accelerated enough, they won't gain enough kinetic energy, then they won't be able to break the bonds. Till that point of time, it's fine. But once they gain that energy, for them to gain that energy, they need certain voltage. Once they gain that, once the voltage, reverse bias voltage is that much, then they have gained enough kinetic energy, it becomes dangerous. Look, for this voltage, no, they didn't gain. For this voltage, they gained. All of a sudden, lot of free electrons get created. That's why you get lot of current, because you have lot of free electrons. And because of this avalanche breakdown, the whole diode gets destroyed. Avalanche breakdown is bad. Okay. Let's do some questions. Which of the following circuits is reverse biased? What is reverse biased? Lokesh Mahesh, sir, you're Telugu. Yes, I am from Andhra. My mother tongue is Telugu. Okay, now come on. When I say reverse biased, P-type semiconductor should be at lower potential, N-type should be at higher potential. Okay, let me mark that. We have this to be +2, this to be -10. That means this is connected to lower potential, this is connected to higher potential. No, this is forward biased actually. Instead of marking cross, I'll just put that this is forward biased. Okay, earth end means 0 and this is -5. 0 is better than -5. So this is forward biased. +2, 0, yes. This is at higher potential. This is at lower potential. So what I can do? I can say that this is in forward bias. Next, you have 2 and +4. +4 is greater. So this is at higher potential side and this is at lower potential side. So you can say that this is reverse biased. So answer is this. Okay, get me the answer for this. And one more thing, whenever a diode is reverse biased, you can say that the current flowing is almost 0. Whenever there is a diode forward bias, you take that it is going to be allowing current just like a normal conducting wire. So I'll just write that point over here if needed. If nothing about diode is mentioned, then under forward bias condition, replace the diode with conducting wire. If it is a reverse biased one, then you have to replace the diode with an open circuit because it won't allow current to flow. Keep that in mind. Now you solve it. This. If you look at what about this diode, is it forward bias or reverse bias? This is -6, this is -8, right? So obviously this end is at higher potential, this end is at lower potential. That means this one is forward bias. What about this fellow? This poor fellow is reverse bias. If it is reverse bias, it will not allow any current to flow. If this is not allowing any current to flow, then this resistance is waste because it is going to be open circuit. So you can simply say that from where the current is going to flow, current is going to flow from this 15 ohms and current is going to flow from this 10 ohms. That's it. So in that case, net resistance is going to be, the R equivalent is going to be 15 into 10 divided by 15 plus 10. So you get 150 divided by 25. So 5 30s, 5 5s and 5 6 times. So the equivalent resistance is 6 ohms. The equivalent resistance is 6 ohms. This branch is waste. It doesn't allow any current at all. Okay, next. Same story, man. Same story. Here also they haven't mentioned which diode they are talking about. Here also they are not talking about which diode they are talking about. So if it is forward biased, replace it with conducting wire. If it is reverse biased, remove that branch. Okay, I can see that 10 volt positive terminal on this side. So this is at higher potential. This is at lower potential. Right? Now if you see, this diode is forward biased. Why? P is at higher potential, N is at lower potential. So this is forward bias. Right? Now, obviously this is connected to the positive terminal. So this also you can write higher potential, lower potential, lower potential. Now if you see properly, what is happening? This diode, lower potential, higher potential. So this is reverse biased. So it will not allow any current to flow. That means this whole branch is waste. This whole branch is waste. It doesn't allow any current to flow in that side. This one forward bias. Now we can draw it properly. Whatever the forward biased ones are going to be there, those you replace with conducting wire. Whatever the reverse bias ones are going to be there, that branch itself you don't draw. That branch itself you don't draw. You have this to be 10 ohms. If you observe properly, these two are in parallel only, man. Those two are in parallel, and this is a 10 volt battery. And what they are asking, current I through the battery. So what is the equivalent resistance? 10 and 10 in parallel. It's going to be how much? 5. So the current drawn from the battery is voltage of the battery by the equivalent resistance, which will turn out to be how much? 2 ampere. So the answer to this question is 2 ampere. Answer to this question is 2 ampere. Okay. Now, applications of this PN junction diode. Applications of this PN junction diode. We can use PN junction diode as a rectifier. What is rectifier? What is rectifier? A device which converts AC to DC. What is rectifier? It converts AC to DC. So when I am going to talk about DC, mainly there will be two characteristics for the DC. One is going to be unidirectional current, other is going to be constant current. So when I say DC, what does DC mean? Unidirectional current. And second is going to be constant current. Then only we call it to be DC. So with the help of this rectifier along with filter circuit, we can convert it into DC. So what is filter circuit? We'll talk about it. But first of all, let us see what the diode is going to do. For that, I have taken a setup. This is the transformer, right? We are feeding in energy, AC, and the output that is going to come out of the transformer is also AC. Right? Now look. potential at A, voltage at A is represented. Voltage at A is said to be positive, and these idiots should have given, this is from NCERT only. Let's take potential at B to be 0, only then you will understand. Now look, when compared with potential at B, if potential at A, if it is positive, if potential at A is positive, then potential at A is higher when compared with potential at B, then this diode is forward biased. If potential at A is more than potential at B, then diode is forward biased. And if potential at A is less than the potential at B, then the diode is reverse biased, then it will not allow any current to flow. Okay, let us look. So when the voltage at A is positive, when the voltage at A is positive, obviously it will allow current, right? As a result, how the current is going to flow? The current is going to flow from X to Y. And that RL is called as load resistance. So you don't need to worry. You just look at the direction of current because we are trying to convert it to AC. That means we need to get unidirectional current. Now, if you are going to talk about the negative half cycle, for the negative half cycle, as this diode is reverse biased, will it allow any current? No. That's why you don't have any output. Voltage across X and Y is going to be called as the output voltage. When current flows through this, then only we will have output voltage. When current is not allowed to flow through this, then you will not have any output. So for the negative half cycle, as VA is negative, VB is 0, this is reverse bias, no current flows. So as no current flows, we have 0 voltage across the load. Now again, when the voltage becomes positive, again the diode will allow current. We got this cycle. And again, when the cycle became negative, potential at A is negative, lower potential, higher potential, reverse bias, no current allowed, no current allowed, no potential drop. So what is happening, man? If any current is allowed to flow through this RL, it is the current which is flowing from X to Y. So did we attain unidirectional current? Yes. Okay, we got unidirectional current, right? So one part is satisfied, but one biggest problem with this kind of rectification is that half cycles are lost. That means that energy is not being utilized, and half cycle energy is not being utilized, as this is going to be using only half of the wave. This rectifier is called half wave rectifier. We have a big problem with this. We have a big problem with this, as half of the cycle is getting wasted when you are going to talk about output power to the input power you have supplied to this rectifier. The efficiency is very bad. The efficiency of this is close to some 40.6%. Output power to the input power ratio, if you are going to look at it, is roughly around 40.6. It's waste, so we are not going to use this. So somehow I have to make sure that even the negative half cycle has to be taken into account. That's when they went for full wave rectifier. How a full wave rectifier is going to look like? It's going to look like this. They are going to take two diodes and they do tapping to the center. Look. Look at the connections. Please be careful with the connections. Now, when A is in the positive half cycle, B is in the negative half cycle. Just keep that in mind. That means, look here, as it is earth end. So you can say this end side and this end side are literally connected to the earth. That means 0. You can say these sides, these n sides, whatever are there, they are both connected to earth. So you can say 0. Now, if A is positive, then this is forward biased, then it will allow current to flow, right? So when this is allowing the current to flow, this is reverse biased. Why? When A is in the positive half cycle, B is in the negative half cycle. That means voltage at B is negative. If this is negative and if this is going to be 0, then this is reverse biased. It won't allow any current to flow. So whatever the current is going to be flowing in this branch, it won't go into this. It will go into this. Okay, nice, good. Now, when we go for the negative half cycle, for A, this A will not allow current, but this one will allow. Why? Then this became positive. Voltage at B became positive and this is 0. Then it will allow current. When it is going to be allowing current, the current is going to go like this and it is going to go like this. So both the yellow and the green ones, are they in the same direction? Yes. So we got unidirectional? Yes. And are we able to get a continuous output? Yes. But one half is contributed by D1 diode, other is contributed by D2, again D1, again D2, like that. But we are utilizing the whole thing. We have a continuous output, but still we are not to the fullest. Why? We want a DC supply, and DC supply means unidirectional current and constant voltage, not a fluctuating voltage. And this is going to be called, this setup is called as full wave rectifier. This setup is called as full wave rectifier, and the efficiency of this is close to some 81.2%. Okay, using this diodes, I converted the current into unidirectional, same direction, x to y only. Now I have to make sure that the voltage becomes constant. For that we use filter circuit, and in the filter circuit we have something, and that something is capacitor. So after diode, after passing through the diodes, that is the rectifier, we add a filter circuit. Now what will happen is, when you are sending an input like this, so as the voltage increases, this capacitor gets charged, and the potential difference across the capacitor and the load are same because they are connected in parallel. So the capacitor gets charged as the voltage increases. So the voltage across the load also increases. As a result, the voltage across the capacitor also increases. That means the capacitor is getting charged. Now, when the input voltage starts decreasing, we have a charged capacitor which is going to be maintaining the voltage across the resistor. Yes, I agree. When the voltage drops, even the capacitor tries to discharge. But if you talk about the time in which it is going to discharge, that time is very big when compared with the cycles of this input. So by the time it has decided to discharge, again the positive cycle kicks in. By the time the capacitor decides to discharge, again the positive cycle kicks in. As a result, what will happen? Roughly, this is charged and it is staying there itself. Roughly it is charged and it is staying at that much voltage only. By the time it feels that, okay, I have to discharge, again the AC cycle will change and it is going to be charging back the capacitor. Roughly the voltage across the capacitor will be constant. As a result, voltage across the resistor will also be what? Constant. Once charged, roughly you can say, you can see actually, but you can see some bumps, right? As I said, yes, it will try to discharge, but by the time it has decided to discharge, immediately the charging process starts, because these cycles are very fast than the discharging cycles of capacitor. So using the capacitor, we are going to roughly maintain the voltage also to be what? Constant. So ultimately, with the diode and with the help of capacitor, an AC has been successfully converted to DC. So there can be theoretical questions on this, but I haven't seen any questions on this in the recent days. I haven't seen any questions on this in the recent days. Okay. Now let me just talk about some optoelectronic devices. Lot of theoretical questions are coming on this part. That's why I have taken it. After my lecture, you don't need to read anything in NCERT also. How much hour is needed for theoretical questions, how much hour is needed for numerical questions, all of it is being covered. You don't need to look somewhere else. Okay, we have seen so far how a semiconductor diode behaves under applied electrical inputs. In this section, we learn about semiconductor diodes in which carriers are generated by photons. And that's the reason why they are going to be called as optoelectronic devices. So what are we going to especially discuss? Photodiodes, LEDs, solar cells. Photodiode, LED and solar cells. Okay, fine. What is a photodiode? Photodiodes are used in fire alarms, man. What happens in fire alarm? In the case of fire creates light, and that light is going to fall onto a diode, and that diode triggers some signal. To trigger some signal, there should be some current flow. So photodiodes exactly do that. So what is a photodiode? Let's see that. Man, on the depletion region, 1 second. You can see the simulation. On the depletion region, light strikes. That means photons strike. Photons are going to come and strike. When they strike, a hole and an electron gets created, because when you give energy, obviously electron takes it and it becomes free. Once it is going to become free, a free electron and a hole are going to get created. And you know very well that in that region there will be electric field like this. So the hole will be made to go like this and the electron will be made to go like this. As a result, there will be some current generated. As a result, there will be some current which is going to get generated. I'll represent it over here. So look, on the depletion region, why we have to go for the depletion region? Because in the depletion region only we have the electric field. As a result, when we throw light, electron gets free. Not visible. Electron is going to be taking those photons and it is going to become free. Then hole gets created. Electron will be made to go to this side. Holes will be made to go to this side. Although the current contribution is very less. Array, some 100 photons if they strike also, some 100 electrons, 100 hole pairs will get created. The current created due to photons is very small. In order to detect these small currents, photodiode should be operated. This is one important theoretical question. Should be operated in reverse bias. Should be operated in reverse bias. Why? Example, let us take, if the current due to photon that got created is going to be some 2 microamp, right? Now under forward bias situation, already there will be current which is going to be what, let's say some 3 milliamps. So to this, if 2 microamps gets added, change in current. To this, if 2 microamps gets added, no much difference in current will be felt. No much difference in current will be felt. If you are operating in reverse bias, in reverse bias, the actual current that is going to be already existing, let us take it to be some 1 microamp. To this, if 2 microamps is added, current becomes 3 microamps. You can say the current has tripled. It's easy to detect here, right, than here. There won't be more or less any change in the current. But if you are operating it in reverse bias, current is getting tripled. So it's easy to detect if you operate the photodiode in reverse bias. So one important theoretical question in photodiode is how the photodiode is going to be operated. It will be operated in reverse bias, right? And you can see over here, you can see it over here. The diagram is drawn in reverse bias situation only. And one more thing, when you will have more current, you will have more photocurrent created. If you have more photons thrown is more intensity. More photons thrown is more intensity. Is everyone clear till here? Okay, fine. LEDs. Heavily doped PN junction diode, with forward biasing, is going to be LED, right? Yes, Venkat. Yes. Yes, Mr. Venkat. Why it should be heavily doped? Why it should be heavily doped? No, no, they are not deleted. Someone is asking a question, sir, LEDs are deleted. No, you can see. Okay. When we talk about an LED, if the doping is going to be heavy, exactly whatever happened in the case of photodiode, exact reverse should happen here. What is it? In photodiode, we throw light, current gets created. Here we create current. We expect some of the holes and electrons to recombine. If they recombine, then energy should be released, right? If you give energy, if they are getting split, if they recombine, they should give light energy or photons. So if you have a heavily doped PN junction diode, then we will have higher probability of electron hole recombination resulting in photons being emitted if we make sure that photons to be in visible region, we get to see them. See, I have taken this text from NCERT, and in this somewhere LEDs that can emit red, yellow, orange, green and blue light are commercially available. The semiconductor used for fabrication of visible LEDs must be at least having a band gap of 1.8 electron volt. Why? Whatever the energy gap is going to be there, if you give photon to the electron, then that band gap amount of energy, if you give, electron will go to the conduction band from valence band. So from conduction band, if it is coming back to the valence band, whatever the energy gap is there, that much amount of photon has to be emitted. So if the energy is going to be 1.8 electron volt, then it will be having a wavelength like this, then only we will be able to see. So you can see that the compound semiconductor gallium arsenide phosphide is used for making LEDs of different colors, right? You just have a rough idea about this, but keep one thing in mind. LEDs are very sensitive to reverse biasing. They easily burn out as breakdown voltage is small. Unlike the other diodes, heavily doped diodes will have breakdown voltage small. If you ask me, around 5 volt. So the moment if you apply a 5 volt reverse bias across LED, LEDs are going to be getting destroyed because they undergo breakdown. I'll tell you the reason. If you ever going to do heavy doping, that means there is huge population of majority charge carriers, right? So the majority charge carriers are so strong that the size of the depletion region will be small. For heavily doped materials, size of depletion region is small. As a result, electric field is very big. Why? Huge majority results in huge diffusion. So there will be lot of charges that are going to be present over here. Lot of charges are going to undergo diffusion, and at the same time as these are very high number, so they have a strong urge to go to that side, so they will always be keeping this depletion region as small as possible, because they push from this side, and from this side huge number of electrons, heavily doped, right? As there are huge number of electrons, even these electrons will exert lot of pressure on the depletion region. So from both the sides, they desperately want to go this side, but this depletion region is trying to slow down, or you can say discouraging. So the size of this depletion region will be actually very, very small in the case of heavily doped ones. Keep this in mind. I'm going to use it in GNO diode. Keep this in mind. I'm going to use it in GNO diode. Venkat is asking questions, sir. When will you be teaching logic gates? I'll be doing logic gates in the next class. I think if it is going to be touching 8, then I'll shift even GNO diode to the next class, because I want to balance the class timing. I don't want to overdo in one class, and I don't want to do very less in the next class. So I'll balance it off, so that people who are going to be watching also, it will be easy for them. Okay, now one thing which I have clearly said to you is that if you are going to be doing heavy doping, this is the situation. You have strong electric field. Why the electric field is strong? Obviously, you have more charges and less gap between them, indicating strong electric field. Now the electric field is already strong. If you connect a battery in the reverse bias to this one, then that electric field of the battery is also supporting the minority charge carriers. Already there is a strong electric field. To that, if you connect a battery which is going to be aiding this electric field, then what will happen? The minority charge carriers will get huge acceleration. If they get huge acceleration, what will happen, man? They gain lot of kinetic energy. If they gain lot of kinetic energy, they collide, avalanche breakdown. Right? That's why LEDs are very cheap. You do one thing, you buy an LED, but instead of connecting the positive terminal, when you buy an LED, you will have one long wire and one short wire, trying to indicate which one is positive, which one is negative. Instead of connecting positive, you just reverse bias, like you connect the connection in a reverse way. You will see that the diode is going to get destroyed. That LED light is going to get destroyed. It get what we call, it will burn out. So be careful. Okay, fine. And one more thing, how the LED is operated. LED is operated in the forward bias. Keep that in mind. Why we have to go for forward bias? In forward bias, lot of charges are going to move. When we make lot of charges to be moving, there is high possibility that there is electron hole recombination taking place. When they recombine, the free electron is now going back to the valence band. When the free electron from the conduction band goes to the valence band, it has to give out energy. If that energy is going to be in the visible region, we will be able to see them. That's it. Take this question. A light emitting diode is fabricated using gallium arsenic semiconducting material whose band gap, that means, look, if this is the conduction band, if this is the valence band, then the electrons, the free electrons, when they fall back, they should give away energy. How much energy? Photon. 1.42 electron volt energy photon can be taken as some 12,000 or 1240 electron volt nanometer divided by wavelength, because I have taken energy of photon. Now the wavelength of light that is going to come out is 1240 by 1.42 nanometers. 1240 divided by 1.42, which will be 873 roughly. So 873 nanometers. Which option is close to 873, 875? Okay, so this is about LEDs. Now let us talk about solar cells. Photodiode, reverse biased. LED, forward biased. Solar cell, no biasing at all. And if you ask me, photodiode and solar cell are going to be operating on the same principle. Only thing is that there is no biasing at all. So in photodiode, what will happen? Light will go and strike depletion region, and electron is going to be freed from that bond in the depletion region. As already an electric field is existing in the depletion region, that electric field will separate the electrons and holes. Holes will be made to go to the positive side. Electrons will be made to go to the negative side. So if that process keeps happening, you can say that the positive side is going to and the negative side is going to have some charges induced. As a result, there will be some EMF developed. So across that EMF, if you connect some resistance, then current will flow. That's what a solar cell is going to do. Look, everything is explained in this GIF. Photons are going to be striking the depletion region, and in the depletion region, whatever the holes and electrons are going to get created because of the electric field in the depletion region, they get separated. You can see electrons, those electrons and protons, whatever holes, whatever are there, they create EMF. Look, electrons, holes got created. So there is some potential difference or EMF across these ends. So if you connect your phone across, obviously as there is some EMF, your phone is going to get charged because current is going to flow. So in order to understand, look, so this is the GIF. You can see we are throwing photons onto the depletion region. Then those photons will be taken by some of the electrons, and those electrons get free. When the electron is going to get free, obviously a hole also gets created, and in this region we have already some electric field. So that electric field will apply force on the electron to the right side and on the hole to the left side. As a result, holes accumulate on this side, electrons accumulate onto this side. As a result, there will be some EMF which is going to be developed across the ends of the diode. Now, if that diode is going to be connected across a resistor, as there is EMF, some current will flow. So how are the characteristics? The current versus the voltage. So you can see here, current is zero. That means we are talking about open circuit. Current zero means we are not connecting anything. Then you get the EMF developed across this. That's the voltage they have mentioned. Now, when I remove this resistor and put it as a conducting wire, then the potential difference will become zero and there will be current, huge current flowing. That is what. So you have the graph in the fourth quadrant if it is going to be a solar cell. Why they have drawn it in the fourth quadrant? Why not here? Why not here? Or why not here? Right? Look, this quadrant and this quadrant we have already used to explain the properties of the to explain the properties of the diode. When the current is created by the battery, we have used this. But here, diode itself is the battery. So I have to draw it in some other quadrant such that this is a special case. People will feel that it is a special case. That's why we have chosen the fourth quadrant. So the graph will be asked for solar cell. Now look, there will be one common question which is going to be asked. Let me just take out that from NCRT. Okay. See, if the energy gap is less, I'm talking about a question from NCRT itself, I'm putting it in the layman terms. If the energy gap is less, it's easy to free an electron or not. If Eg is less, it's easy to free electron and develop EMF across the diode. Now, this NCRT question, look, PBS has an energy gap of roughly 0.4 electron volt. And then if you talk about the energy gap for silica, the energy gap for silica is roughly 1.1 electron volt. And the energy gap for gallium arsenic is roughly 1.5 electron volt. So the energy gap is lowest for PBS when compared with silica and gallium and arsenic. So it's easy to free electron over there. It's easy to free electron from PBS. But we make solar panels with silica. Majority of the times we make with gallium arsenic than silica. Like, because they have good absorption. Then why not use this? It's very easy to free, right? It's very easy to free the electron here because the gap is very less. So it's easy to make the electron go up. Once they become free, EMF gets induced. Look, first the problem with this one is that as the gap is very less, as the energy gap is very less, majority of photons don't go to depletion region. They will be absorbed in between only. Look, for us to get that EMF developed, the photons whatever we throw should be able to reach the depletion region. So if the photons I send, if the photons I am going to be sending are absorbed by this region majorly, electron hole are going to get generated, but they don't go anywhere. They won't create much of a difference. But if the photons go and strike here and make one electron and hole free, as there is electric field in the depletion region that makes those charges separate. So EMF will get induced. But if those electron hole pair gets created here, it's of no use. There is no electric field to separate them and make EMF induce. So that's why we won't choose PBS. If it is silica or gallium arsenic, it's not that easy to make the electrons free. So some of the photons are definitely going to go to the depletion region. Some are definitely going to be absorbed in this region also, but some are going to go to the depletion region. There is high possibility. As a result, we choose these things. Now, why are we going to choose 1.5 electron volt only? Whatever the radiation that comes out from the sun, if you trap it and if you look at, majority of the radiation has 1.5 electron volt. energy. That means out of 100 photons that are reaching the earth, some 20-30 belong to 1.5 electron volt. Some 20-30 belong to 1.5 electron volt. So majority of the photons will belong to this region. So we should always choose that particular solar cell where the energy gap is less than 1.5 electron volt. Then it is easily made free. It should not be too less. If it is too less also, then majority of the photons will be taken by these layers only. They won't be allowed to go towards the depletion region. Now if you look it in that way, silica is better than gallium arsenic. Na? Why? It is not too small and at the same time it is very close to 1.5. Then why we prefer this than this means gallium arsenic has more absorption coefficient. That means if you throw some radiation, some gets reflected, some gets absorbed. Gallium arsenic has higher absorptive coefficient. That's why if you want higher efficiency solar cells, people prefer gallium arsenic. Okay, fine. Theory has been done. So next part is going to be Zener diode and logic gates. So we have, how many slides we have completed? We have completed around 57. We have 83. So how many are pending? 26 slides are pending. So I'll be doing them tomorrow. As it is a theoretical one, giving too much of content in a single day also is going to fry your brain. So whatever I have given, and this whole PDF will be shared at once. For your comfort. You don't need to search. So you won't get this PDF today. Tomorrow after the class is done, I'll share the whole PDF at the same time. Okay, keep working hard. Man, one thing, if you have any doubt, please re-watch the video or you go back in time and watch the video. As a result, you will get more and more clarity. I have lot of in-depth conceptual understanding of this semiconductors. If you have any problem, do comment below. I'll reply to the comments. Good night.